Okay, so to first understand buoyant force, we need to talk about pressure. Now, pressure is force over an area. Newtons over meters squared will give you pascals, and that's the standard international. Now, to kind of explain this further, let's say you have that, same amount of force, F sub G, you weigh what you weigh. But if you're wearing loafers or tennis shoes, you've got a larger area that your force is over. If you're wearing high heels, you just have a tiny little area, the toe, that all that force is on. And so there's a lot of pressure there, and high heels are not very comfortable. Another reason that laying down is much more restful than standing up is that you're putting your weight, your F sub G, your newtons, over a larger area, so the pressure is less. Now, to find a pressure under a fluid, you take the density of the fluid, and the units there are going to be kilograms over meters cubed. I don't know if we can write that in. Kilograms over meters cubed. And I lost my stylus, so it's my finger there. The depth of the object in meters, and then the gravitational pull. And if you look at those units, you're going to get newtons over meters squared. Now, liquid pressure only depends on the depth of the object, not how much total volume there is. Therefore, a fish at the bottom of a narrow tube of 5 meters deep is feeling the same pressure that he would at the bottom of a 5-meter deep, huge reservoir of water. So what we're looking here basically is the depth of the object, not how much total volume there is. Now, buoyant force comes about because there is less pressure here and more pressure here because the bottom of the object is deeper, and so you have more pressure there. Now, this pressure differential leads to the buoyant force. Okay, and it doesn't matter how deep you are. You could be 1 meter under the water, or you could be 20 meters under the water. The buoyant force will be the same because the pressure differential is the same. Now, the deeper you are, of course, the greater these pressures are going to be, but the difference in the pressures will be the same, and so the buoyant force will be the same. Archimedes' principle is going to be the basis for all the mathematics here. The buoyant force, the immersed body buoyed up by a force, that's your buoyant force, is going to be equal to the weight of the fluid it displaces. The weight of the fluid. So circle those words. That is what we're going to focus in on. And the Eureka straw, you can look up the Archimedes. All right, now we have the weight of an object. Wonderful. It has nothing to do with the buoyant force. Focus on the fluid displaced, specifically the weight of the fluid displaced for F sub B. Remember, air can be a fluid too. For F sub G, we just find F sub G like we always have. But F sub G, the weight of the object, has nothing to do with the buoyant force. Now, the volume of the object will, because the volume of the object will determine how much fluid is displaced, and then, of course, the weight of the fluid is our buoyant force. But we have to be careful, it has nothing to do with the weight of the object. If the object's weight is greater than the buoyant force, the object will sink. If it's less than the buoyant force, the object will rise. And if the object's weight is equal to the buoyant force, the object stays where it is. It is called neutrally buoyant. Now, if an object is floating, the F sub G will equal the F sub B. The buoyant force will equal the weight, and the object will be floating. Some examples of adjusting F sub B and F sub D. Fish adjusting its swim bladder, it puts more air into its swim bladder, becomes lighter, it adjusts its F sub G. It might displace a little bit more water, it might swell up a little bit, so that would affect the buoyant force because more fluid is displaced. But I think with this that the fish really are adjusting its weight, okay? And then of course its buoyant force is however much fluid it can displace. The density of a person decreases by putting on a life jacket. When you put on a life jacket, you expand how big you are. You're much bigger. And so when you're in the water, you displace a whole lot more water, but you're not adding a lot of weight. Life jackets don't weigh very much. You put it on, you don't add a lot of weight to yourself, but you are displacing a whole lot more water, so your buoyant force goes up. Submarines are going to adjust their F sub G by letting water in or out of the hulls to rise or fall. Crocodiles swallowing stones, they're also adjusting their F sub G. Iron ships displace a lot of water to get a large buoyant force. So I have a 10,000 ton ship. If I want it to float, I have to displace at least 10,000 tons of water. So when I build the ship, I want to make sure that if this ship is 10,000 tons, I want to make sure when I build it, that when I build it, it displaces or pushes out of the way 10,000 tons of water. Get that out of the way, then the 10,000 ton ship will float. And of course you want to do more than 10,000 because you don't want the water level to be right at the edge here. Okay, so you want to, if you're a 10,000 ton ship, you want to make sure you displace a whole lot more water so that you're not floating right at the edge. You're displacing it. Okay, so we're going to take a look at some examples. I've got a cubic meter block of aluminum half submerged. So when I talk about this, please be careful. It's not necessarily floating, okay? We're just submerging half of it. So be careful just to assume that things in water are necessarily floating. Unless they say they're floating, don't assume it. I'm just going to take it, I'm going to have a hook on it, I'm going to put it in some water, it's half submerged. It's going to displace 0.5 cubic meters of water. Now, what is the buoyant force? I don't care, it's aluminum. If I want to find the buoyant force, this can be made out of anything. The biggest part to me is that it's displacing 0.5 cubic meters of water. Now, that's not what Archimedes said, though. He did talk about the fluid, the water. But he didn't talk about the volume of water displaced. He talked about the weight of the water displaced. So to get from kilograms to cubic meters, I'm going to have to go ahead and multiply by the density of fresh water. So I get 500 kilograms. Now, to actually find a force, of course, this is a mass. I'm going to multiply by 9.8 meters per second squared. And I'm going to get 4,900 newtons of force. That is the buoyant force. Has absolutely nothing to do with aluminum, the weight of aluminum. We may want to calculate that, but that is not what's being asked. Now, I have a cubic meter block of iron, and it's completely submerged in water. Now, we know if we let that go, it would sink, right? But we're just going to hang it in water. The whole thing, this is the water level, actually. And the whole thing is submerged, this whole cubic meter of iron. All right, well, what's the buoyant force? Again, just to find the buoyant force, I don't really care that it's iron. It doesn't matter what it is. A cubic meter of it is being displaced. So again, I'm going to take 1,000 kilograms per cubic meter, and I'm going to get 1,000 kilograms of water displaced. Then I multiply by 9.8, 9,800 newtons of buoyant force. Okay? Now, you could ask about its weight. That's another legitimate question. And in fact, if we want to know if this thing will sink or if it will rise or if it will just stay put, we may want to know that. Nothing to do with the buoyant force, but we may want to know that. So I've got a cubic meter of iron. So what I want to do here basically is find the density of iron, which I'm going to go off memory here, but I think it's 7,890 kilograms per cubic meter. So to find F sub G, I've got 7,890 kilograms times 9.8. So it's like 77,000 newtons is its F sub G. 77,000 newtons. And its buoyant force is only 9,800 newtons. So it certainly isn't as heavy in water as it is in air because we have this buoyant force, but it certainly is going to sink if I let that go. We know. F sub G is a lot greater than F sub B.